Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us out into the vastness, to the distant, russet world of colonizing Mars. The red planet hangs in the deep velvet of space, a silent neighbor looking back at our own blue world. It has waited for millennia, a keeper of iron-rich dust and frozen canyons. Tonight, we are not going there to conquer or to rush, but to dream. We will drift across the great, cold silence that separates our home from this new shore, letting our minds wander through the possibilities, the challenges, and the immense, quiet beauty of a world that is not our own. Let the noise of the day fade away, replaced by the soft whisper of the solar wind and the turning of these two great spheres in the dark. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. Mars does not have a global magnetic field to protect it from harmful solar radiation. We often take for granted the invisible shield enveloping our own world, a magnetic cocoon spun by the churning iron core of Earth, which diligently catches the high-energy particles streaming from the sun. This solar wind, a relentless force, is deflected, creating the beautiful auroras at our poles, but otherwise leaving us unharmed. Mars, however, is not so fortunate. Its own core has long since cooled and quieted, its dynamo falling silent billions of years ago. The planet, stripped of this vital defense, lies exposed. Any colonists on its surface would face a constant, invisible rain of galactic cosmic rays and solar protons, particles that can quietly damage living tissue and unravel the delicate script of DNA over time. Protecting human life there requires us to become the architects of our own shield, perhaps by burying habitats beneath the rust-colored soil, letting the planet itself become the guardian, or by constructing bases within lava tubes, ancient volcanic tunnels that now offer a quiet, dark sanctuary from the harsh radiance of the unfiltered sun. This challenge is not one of violence, but of ingenuity, a call to understand the cosmic weather and to build a new kind of shelter, turning rock and regolith into a cradle for fragile life. The soil on Mars, known as regolith, is toxic to Earth-based life due to high concentrations of perchlorates. When humanity first dreams of settling the red planet, we often envision planting gardens, rows of green emerging from the alien soil, a comforting echo of home. But the Martian regolith, that fine, iron-rich dust that blankets the planet, holds a chemical secret that is indifferent to our agricultural hopes. This soil is laced with perchlorates, salts that are profoundly toxic to the microorganisms, plants, and animals of our own biosphere. The very ground, while rich in minerals, would scorch the roots of terrestrial plants and contaminate any water it touches. This is not a malicious act by the planet, but simply a result of its unique chemical history, shaped by ancient briny waters and eons of photochemical reactions under a thin sky. To build a farm on Mars, we cannot simply plant a seed. We must first heal the soil itself. We must invent processes to wash these salts away, perhaps by flushing the regolith with water, or by using specialized microbes that can patiently digest the toxins, transforming the barren dust into a life-giving medium, one handful at a time. A day on Mars, called a sol, is only about 39 minutes longer than an Earth day. The universe, in its grand and often incomprehensible scale, sometimes offers small, comforting coincidences. while Mars is a world profoundly different from our own, frozen, thin-aired, and distant. It spins with a rhythm almost familiar to us. An Earth day, defined by the spin of our own cradle, lasts 24 hours, a cycle that has governed life's rhythms for billions of years. Mars, turning just a fraction slower, completes its own rotation in 24 hours, 39 minutes, and 35 seconds. This small gift, this near synchronicity, means that the cycle of light and shadow, the rising and setting of a smaller, distant sun, would feel almost like home. The human body, with its deep-seated circadian rhythm, would find this new tempo far easier to adopt than the perpetual night of the moon or the rapid spin of other worlds. It allows the dream of colonization to feel more tangible, a place where our internal clocks would not be hopelessly lost, but merely asked to slow their pace just a little, settling into the gentle, slightly longer breath of a Martian soul. The average temperature on Mars is a harsh negative 63 degrees Celsius, or negative 81 degrees Fahrenheit. We see the red planet as a place of warmth, its color palette of rust and amber suggesting a desert heat. But this is an illusion of distance. Mars is a world of profound, penetrating cold. Its thin atmosphere, a whisper of carbon dioxide 100 times less dense than Earth's, cannot hold the sun's gentle warmth. When the small, pale sun sinks below the horizon, any heat gathered during the day radiates away quickly into the blackness of space, leaving the surface to plunge into temperatures that can freeze carbon dioxide solid at the poles. Colonists would live in a world where the very air outside their habitats is a thermal void, a place where survival is not just about breathing, but about a constant, determined effort to hold on to warmth. Their homes would need to be bastions of heat, insulated and powered, existing as tiny islands of temperate life in an ocean of cold, a testament to the fragility of warmth and the resilience of the mean that learns to harvest it from faint sunlight or the planet's own sleeping core. The gravity on Mars is only about 38% of Earth's. Imagine taking a step and feeling a strange, gentle buoyancy, a lifting of the profound weight you have carried your entire life. On Mars, the planet's smaller size and lesser mass exert a weaker, softer pull. A person weighing 100 pounds on Earth would feel as if they weighed only 38 pounds on Mars, granting them a new, dreamlike physicality. They could leap higher, lift heavier objects with ease, and move with a loping, graceful gait. This is the promise of a low-gravity world, a reduction of the constant strain on our bones and our hearts. Yet this gentle pull is also a profound biological challenge. The human body is a structure shaped by Earth's gravity. Our muscles are toned to fight it, our bones dense to support us within it. In the long term, this lightness would cause our bodies to adapt, our bones to thin, and our muscles to weaken, as they surrender to a world that asks less of them. We would have to relearn how to live, perhaps spending hours in centrifuges or under heavy compression, to remind ourselves of the home they left behind, all while floating through a world that invites us to forget. Mars has two small, irregularly shaped moons named Phobos and Deimos. Unlike our own singular steady moon, a perfect silver disk that governs our tides and lights our nights, Mars possesses two more chaotic companions, Phobos, meaning fear, and Deimos, meaning terror, are not majestic spheres but captured asteroids, potato-shaped rocks of darkness tumbling through the sky. They are small, barely mountains by planetary standards, and they move with a hurried, unusual pace. Phobos, the inner moon, whips around Mars faster than the planet itself rotates, rising in the west and setting in the east, sometimes twice in a single sol. Deimos, farther out, drifts more slowly, a tiny point of light lingering in the sky for days at a time. For a colonist standing on the surface, these two moons would be a constant, dynamic presence, a celestial dance of two captured nomads, reminders that not all things in the universe are formed in gentle orbits, but are sometimes caught and held by unseen forces. The planet is home to Olympus Mons, the largest volcano in the entire solar system. On Earth, our mountains are ancient and weathered, pushed up by colliding continents and worn down by wind and rain. On Mars, a different kind of geology, driven by a stable crust and a weaker pull of gravity, has allowed mountains to grow to scales that defy our terrestrial imagination. Olympus Mons is not merely a mountain. It is a shield volcano so vast, it would cover the entire state of Arizona, its base sprawling over 600 kilometers wide. It rises about 25 kilometers, 3 times the height of Mount Everest, piercing the thin Martian sky to such a degree that its peak often sits above the planet's dust storms. Standing at its base, one would not even perceive it as a mountain. Its slope is so gentle, it would feel like standing on a vast, imperceptibly rising plain. It is a monument built by 1 billion years of patient, steady volcanic pulses, a testament to the power of a world's hidden warmth, now sleeping, but leaving behind a scar of truly solar system spanning proportions. Evidence suggests that liquid water once flowed freely, carving vast canyons and riverbeds on the Martian surface. Today, Mars is a frozen desert, its water locked away in polar ice caps or buried as permafrost deep beneath the dust. Yet the planet's surface tells a story of a much different, warmer, and wetter past. When we look down from orbit, we see not just craters, but the unmistakable branching patterns of ancient river deltas, the dry, meandering beds of long-vanished streams, and the sheer, dramatic cliffs of canyons like valles marineris, which were carved not just by tectonic rifting, but by catastrophic outflows of water. Billions of years ago, a thicker atmosphere, a warmer climate, and perhaps even a vast northern ocean made Mars a blue planet, a sister to our own. The wind that now blows only dust once pushed waves across a liquid sea. Colonizing Mars is therefore not just an act of new construction, but an act of archaeology, a journey to a world of ruins, where we seek to understand the great climate transformation that silenced its rivers and left only their beautiful, silent echoes behind. The atmosphere of Mars is over 95% carbon dioxide. We breathe an atmosphere that is a complex, nurturing blend, a nitrogen-rich cushion with a vital helping of oxygen, a gas exhaled by the very plants that share our world. The air on Mars is profoundly different. It is a thin, stark, and alien medium, composed almost entirely of carbon dioxide. It is the exhalation of a planet that has long since stopped breathing in a biological sense. This air is unbreathable to us, and it is so thin that liquid water cannot exist on the surface. It boils away almost instantly in the low pressure. To walk on Mars, humanity must remain encapsulated, carrying our own small bubbles of Earth's sky with us. The challenge of colonization is the challenge of atmospheric alchemy, to take this abundant but useless carbon dioxide and find ways to split it, to harvest its hidden oxygen atoms, and to slowly, painstakingly begin the process of weaving a new sky, one that we, and perhaps future Martian-born plants, might one day recognize as air. Dust storms on Mars can grow to envelop the entire planet for weeks. The red planet is a world of dust, a fine iron oxide powder that covers everything, staining the landscape in hues of ochre and rust. This dust, energized by the faint sunlight and the temperature differences across the planet, is easily lifted by the wind. While the winds are thin, they are persistent, and they can conspire to create storms of unimaginable scale. Unlike an earthly storm, which is a regional event, a Martian dust storm can grow, feeding on itself until it becomes a global phenomenon, a planet-encircling shroud. The sky turns a dark, reddish-brown, sunlight is reduced to a dim twilight, and solar panels are rendered almost useless, choked by a blanket of fine powder. For colonists, these storms would be a time of retreat, a long, quiet hibernation, as they listen to the faint, eerie sound of the wind scouring the world outside their habitats, a reminder that the planet's weather, though thin, possesses a powerful, patient ability to erase and conceal. Valles Marineris is a system of canyons that dwarfs Earth's Grand Canyon. We look upon our own Grand Canyon with awe, a mile-deep chasm carved by the patient work of a single river over millions of years. On Mars, the planet's tectonic stresses have created a scar so profound it makes our own wonder seem modest. Valles Marineris is not a single canyon, but a vast network of interconnected chasms that stretches for over 4,000 kilometers, the distance from Los Angeles to New York. It is 7 kilometers deep in places, and so wide that if you stood on one rim, you would not even be able to see the opposite side. This is not only a canyon carved by water, but a great crack in the Martian crust, a place where the planet itself split open as the nearby Tharsis volcanic bulge pushed the surface upward. It is a landscape of impossible scale, a wound on the planet that invites exploration, a place where colonists could fly aircraft through its deep valleys, protected from surface radiation, exploring billions of years of geological history laid bare in its towering silent walls. Terraforming Mars, the process of making it Earth-like, would take centuries or even millennia. The dream of a green Mars is a powerful one, an image of blue skies, open oceans, and forests sighing in the wind. But the process of achieving this, of transforming a frozen, low-pressure world into a garden, is a task of geological time. Terraforming is not a simple project. It is an act of planetary engineering on a scale humanity has never attempted. It would require us to first warm the planet, perhaps by releasing potent greenhouse gases stored in the soil, or by importing them from elsewhere in the solar system, just to melt the frozen carbon dioxide at the poles. This would thicken the atmosphere, which would trap more heat, which would melt the water ice, creating a feedback loop of warming. Only after centuries of this slow planetary simmering would the pressure be high enough for liquid water to exist, and only then could we begin the even slower process of introducing microbes and plants to create a breathable oxygen atmosphere. It is a project not for us, but for our descendants many generations removed, a legacy of patience. Martian blueberries are not fruits, but small hematite-rich spheres found by the Opportunity rover. In 2004, a small 6-wheeled rover exploring the plains of Meridiani Planum sent back images that delighted and puzzled scientists. The ground was covered in countless tiny grey-blue spheres, nicknamed blueberries. These were not the soft, sweet fruits of an alien bush, but hard, geological concretions, small pebbles rich in the iron-bearing mineral hematite. Their nearly spherical shape and their presence within layered rock formations told a profound story. On Earth, such hematite concretions typically form in the presence of abundant liquid water, as minerals precipitate out of solution and build up in a spherical pattern. These tiny stones were therefore not food, but fossils of a wetter past. Hard evidence that the arid, dusty plain the rover was crossing had once been a shallow, perhaps acidic, sea. They were a message from Mars's history, a confirmation that the essential ingredient for life as we know it was once plentiful on the surface. Growing food on Mars would require pressurized, artificially lit hydroponic or aeroponic facilities. The surface of Mars is hostile to Earth's plant life. The soil is toxic, the water is frozen solid, the air is unbreathable carbon dioxide, and the unfiltered radiation would damage delicate cellular structures. To feed a colony, we cannot rely on open fields and gentle rain. We must build oases of technology, pressurized greenhouses that replicate the conditions of an earthly spring day every single day. Inside these glowing biodomes, plants would not grow in soil, but in systems of hydroponics, their roots dangling in nutrient-rich water, or aeroponics, where they are misted with a precise fog of fertilizers. Light would not come solely from the distant, dim sun, but from arrays of soft, efficient LED lights, tuned to the exact wavelengths that plants crave. This would be a new kind of agriculture, a closed-loop system where every drop of water is recycled, every breath of human exhalation is fed to the plants, and every plant's breath, in turn, provides oxygen for the colonists. A perfect, fragile symbiosis engineered far from home. The risk of back contamination, bringing Martian microbes to Earth, is a serious planetary protection concern. While we venture to Mars seeking signs of life, we must also consider the profound responsibility of our journey. The scientific community operates under a principle of planetary protection, a two-way street of caution. The first concern is forward contamination, ensuring that our rovers and landers do not accidentally carry hardy Earth microbes to Mars, which could hopelessly confuse our search for native life. But an equally serious concern is back contamination. If we were to find microbial life on Mars and bring samples back, or if colonists were to return, we would have to be absolutely certain that these alien life forms, which evolved in a completely different environment, pose no threat to Earth. Any return samples or crews would undergo rigorous, long-term quarantine in specialized facilities, ensuring that the story of our journey to Mars does not end with an unintended impact on our own home. The psychological toll of isolation on a small crew for years is one of the greatest challenges. We can engineer life support systems, build radiation shields, and calculate orbital trajectories with astonishing precision. But the one variable we cannot easily solve for is the human heart. A mission to Mars, and especially the first colony, would be one of the most isolating experiences in human history. A small group of people would be confined to a small, enclosed habitat, a tiny bubble of life in an endless lethal desert, with their home planet reduced to a pale blue dot in the sky. Communication with Earth would be delayed by up to about 45 minutes for a round trip, making real-time conversation impossible and transforming dialogues into a series of recorded messages. The stress, the confinement, the distance, and the knowledge that rescue is impossible would place an immense burden on the mental health of the crew. Their survival would depend not just on their technical skills, but on their emotional resilience, their empathy, and their ability to find purpose and community millions of miles from everything they have ever known. It would take approximately 7 to 9 months to travel from Earth to Mars using current propulsion technology. The journey between our world and the red planet is not a simple straight line, but a long curving dance governed by orbital mechanics. We cannot simply point a rocket and go. We must wait for the precise moment when the two planets are aligned in their orbits, a launch window that opens only once every 26 months. Once that journey begins, astronauts are not truly flying, but coasting. After a powerful initial burn to escape Earth's gravity, the spacecraft spends the vast majority of its voyage in freefall, drifting silently through the interplanetary void, following a wide arcing path called a Hohmann transfer orbit. This 7 to 9 month drift is a period of quiet vulnerability, a time spent in zero gravity, exposed to cosmic rays, and utterly reliant on the ship's systems. It is a long crossing that must be made before the planet even comes into view, as more than just a pinprick of red light. The thin Martian atmosphere makes landing spacecraft incredibly difficult and dangerous. Engineers call it the 7 minutes of terror, the harrowing final phase of descent that every Mars lander must endure. Arriving at Mars at over 12,000 miles per hour, a spacecraft has to decelerate to a complete stop on the surface in just minutes. The atmosphere is a paradox. It is too thin to allow for a gentle gliding landing like an airplane, but just thick enough to create immense friction and heat, requiring a massive heat shield. After the heat shield slows the craft, a supersonic parachute must deploy in the thin air, a feat of engineering in itself. But even this parachute is not enough. The air is too wispy to slow the lander sufficiently. The final descent must be managed by retro rockets, a complex sky crane maneuver, or cushioned by airbags. A frantic, automated, and delicate sequence that, due to the light speed delay, must be performed by the spacecraft's own computers with no help from Earth. Mars has polar ice caps similar to Earth's, but they are composed of both water ice and carbon dioxide ice. At the top and bottom of the red planet lie two vast white patches, shimmering against the rust-colored dust. These are the Martian polar caps, Earth's familiar icy cousins, yet they are stranger and more complex than our own. Like Earth, Mars has permanent caps made primarily of water ice, massive frozen reservoirs that hold the planet's hydrological history. But Mars is so cold, especially in winter, that its very atmosphere freezes. The 95% carbon dioxide air precipitates directly onto the surface as snow or frost, creating a seasonal cap of dry ice that covers the water ice. This seasonal cap can grow to be several meters thick, blanketing vast areas. As the Martian spring arrives, this dry ice cap doesn't melt. It sublimates, turning directly from a solid back into a gas, creating geysers of carbon dioxide that erupt through the ice and release dark dust. A seasonal cycle that gently breathes the thin atmosphere in and out each year. All water on the Martian surface is either frozen solid or exists as a very thin, briny vapor. On Earth, water is a liquid, a dynamic, flowing substance that shapes our landscapes and fills our oceans. On Mars, the planet's temperature, and more importantly, its incredibly low atmospheric pressure, make liquid water almost impossible on the surface for any length of time. The pressure is so low that water's boiling point is just above freezing. If you were to pour a cup of water onto the Martian dust, it would simultaneously freeze and boil away into vapor. This means the planet's vast stores of water are locked in forms we cannot easily access, as permafrost frozen harder than granite for miles deep, as the massive polar glaciers, or as a trace amount of vapor in the air. To find liquid water, the kind life needs, colonists would have to search for it deep underground, where the planet's geothermal heat and the immense pressure of the rock above might, just might, allow it to exist in hidden, salty aquifers, precious, concealed reservoirs sleeping beneath the cold desert. A fundamental concept for surviving on Mars is In-Situ Resource Utilization, or the art of living off the land. We are creatures of Earth, accustomed to a world that provides air, water, and food in abundance, a planet teeming with resources that we harvest with ease. But Mars is a world of scarcity, a place where these necessities are not readily available, but locked away in difficult-to-reach forms. In-Situ Resource Utilization, or ISRU, is the philosophy that humanity must adopt to survive there, a promise to not carry our entire world with us, but to become industrial alchemists. It is the practice of harvesting the frozen water ice from the regolith to drink and to split into rocket fuel. It is the act of pulling the thin carbon dioxide from the air to create oxygen to breathe. It is the challenge of taking the toxic, iron-rich dust and learning how to sinter it with heat into bricks, 3D printing our homes and shelters from the very ground we stand on. This is not just an engineering solution, but a profound shift in our relationship with the planet. A move from being visitors to becoming, in the most literal sense, inhabitants who draw their substance from the new world around them. The MOXIE experiment, successfully demonstrated by the Perseverance rover, proved that oxygen can be generated from the Martian atmosphere. The thin air of Mars, a seemingly useless and toxic shroud of carbon dioxide, holds within it a hidden treasure, the oxygen atom. The Mars Oxygen In-Situ Resource Utilization Experiment, or MOXIE, is a small golden box designed to perform a quiet miracle. It works by inhaling the carbon dioxide-rich air and heating it to an extreme temperature, around 800 degrees Celsius. This intense heat, combined with an electrochemical process, cracks the molecules apart, separating the carbon dioxide into carbon monoxide and precious oxygen. MOXIE is a small-scale pioneer, producing only a few grams of oxygen per hour, just enough to sustain a small animal. But as a proof of concept, it is a revolution. It is the first time humanity has manufactured the very air we breathe on another world, a promise that future, larger-scale trees of metal and electricity could one day produce enough oxygen not just for colonists to breathe, but to fill the massive fuel tanks of the rockets that will one day carry them home. Habitats on Mars will likely be 3D printed using the planet's own regolith as the building material. To build a home on Mars, we cannot simply ship lumber and concrete across the solar system. The cost and weight would be astronomical. The solution, therefore, is to build with the material that is already there in abundance, the fine, powdery dust called regolith. This new form of architecture will be robotic. We will send autonomous 3D printing rovers, machines that will crawl the Martian surface, scooping up the local soil. They will then process this regolith, perhaps mixing it with a binding polymer, or using intense microwave or solar heat to melt and fuse the dust particles together, a process called sintering. Layer by layer, these robotic masons will extrude the walls of our first homes, domes, and radiation shelters, building them up from the ground like terrestrial termite mounds. These structures will be a deep red, the color of the planet itself, not just sitting on the landscape but born from it. This is a return to our most ancient form of building, using the local earth to create shelter. But this time, it is an earth millions of miles away, shaped by a digital hand. Martian lava tubes, ancient and hollow volcanic tunnels, may be the safest place for the first human colonies. While the surface of Mars is a beautiful sunlit desert, it is also a place of extreme peril, exposed to unfiltered cosmic rays, wild temperature swings, and micrometeorite impacts. The planet itself, however, offers a solution, a network of natural, pre-built shelters. In Mars's volcanic past, rivers of molten lava once flowed beneath the surface. When the eruptions ceased and the lava drained away, it left behind vast, hollow tunnels, some potentially dozens of meters wide. These lava tubes are geological gifts, subterranean havens that offer a near-perfect sanctuary. The thick ceiling of overlying rock would provide a complete and passive shield against radiation, protecting human and technological life. The temperatures within these caves would be remarkably stable, insulated from the harsh day-night cycle on the surface. We would be following in the footsteps of our earliest ancestors, trading the dangerous openness of the plain for the profound security of the cave, a quiet, dark, and steady place to begin a new civilization. The psychological impact of food monotony is a serious challenge for long-duration Mars missions. We eat not just for fuel, but for comfort, for variety, and for connection to our culture and our home. On Earth, this variety is nearly limitless, a sensory exploration we take for granted. A Mars mission, lasting years, will force colonists into a world of extreme culinary repetition. Their food will be almost entirely pre-packaged, dehydrated, and shelf-stable, designed for maximum nutrition and minimum weight. The joy of a crisp apple, the texture of fresh bread, or the scent of soil on a freshly picked vegetable will be a distant memory. This relentless sameness, those same flavor profiles and textures day after day, can lead to what is called menu fatigue, a condition that causes a loss of appetite, weight loss, and a significant drop in morale. To combat this, colonists must become dedicated gardeners, tending their hydroponic bays not just for calories, but for the psychological relief of a single fresh strawberry, a tomato, or a sprig of mint. Tiny, fragile links to the sensory richness of the world they left behind. The different lengths of the Martian year and day would force colonists to adopt a new calendar, slowly drifting out of sync with Earth. We live our lives by the rhythms of our home planet, a 24-hour day and a 365-day year, a tempo that feels universal and absolute. But this is merely a local truth. On Mars, the slightly longer sol of 24 hours and 39 minutes would create an immediate temporal divergence. A colonist's watch would tick slower than one on Earth, and after just a few weeks, their midnight would be our midday. Furthermore, a Martian year, the long orbit around the Sun, lasts about 687 Earth days, or roughly 668 sols, meaning their seasons are twice as long, their holidays would drift, and their very concept of age would have to be recalibrated. This temporal separation is more than an inconvenience. It is a profound psychological shift. colonists would live in a state of temporal dissonance, forever calculating the time back home, their lives governed by a new, slower, and fundamentally alien clock, a constant reminder that they are no longer living on Earth's time. The 1967 Outer Space Treaty provides the basic and incomplete legal framework for Mars colonization. In the grand silence of space, we often imagine a frontier free of earthly squabbles, but the moment humanity arrives, we will bring our need for rules and property with us. The Outer Space Treaty, a relic of the Cold War, is a document of profound optimism, declaring that space, including Mars, is the province of all humankind, free for exploration by all nations and not subject to national appropriation by claims of sovereignty. This means, quite simply, that no country can plant a flag on Mars and declare it theirs. But the treaty is a document of its time, a skeleton that is silent on the complex realities of colonization. It does not address who owns the resources that are extracted, such as water, ice, or minerals. It does not define the rights of a private corporation that builds a habitat or the legal status of the first child born on Martian soil. The first colony on Mars will not just be an engineering challenge, but a legal one, forcing humanity to draft a new social contract for a new world, built upon the high-minded but beautifully vague principles of a treaty signed before anyone had even stepped on the moon. The philosophical debate between a red Mars and a green Mars defines two possible futures for the planet. When we dream of Mars, we are often split into two distinct camps, a division that goes to the heart of our relationship with the universe. The green Mars advocates are the terraformers, those who see the red planet as a canvas, a fixer-upper, a world to be remade in Earth's image. They dream of thickening the atmosphere, melting the ice, and planting the seeds of a new biosphere, believing it is humanity's destiny to spread life. But there is another, quieter philosophy, that of a red Mars. This view holds that Mars has its own profound, silent beauty, a state of being that is unique in the solar system. To terraform it, they argue, would be an act of cosmic vandalism, erasing billions of years of its geological history. More importantly, if there is any native Martian life, even simple microbes sleeping beneath the ice, then we have a moral obligation to protect it, to study it, and to leave it undisturbed. The first colonists will be the vanguard of this debate, deciding if they are to be gardeners of a new world or the curators of an ancient alien museum. Forward contamination is the profound ethical concern of accidentally introducing Earth microbes to Mars. We are covered, inside and out, with a teeming, invisible ecosystem of bacteria, viruses, and fungi, a microbial cloud that is part of our very being. These microbes are incredibly resilient. Some can survive the vacuum of space, harsh radiation, and cold. The principle of planetary protection, therefore, demands that we act as responsible interplanetary travelers. Forward contamination is the fear that, despite our best efforts to sterilize our landers and rovers, a few of these earthly hitchhikers might survive the journey. If they were to reach a small, habitable niche on Mars, perhaps a pocket of liquid brine, they could begin to grow, multiply, and spread. This would be a scientific tragedy, as it would forever contaminate the Martian environment, making it impossible for us to ever know if a microbe we discover is truly alien or just a long-lost cousin from Earth. Our first exploratory steps must therefore be taken with an almost sterile humility, ensuring that the first life we find on Mars is not, in fact, our own. The average 20-minute communication delay between Earth and Mars would fundamentally change human interaction. We are a species built on near-instant communication, a world where a conversation is a fluid, real-time exchange of ideas, emotions, and support. This connection is maintained by light-speed signals that circle our globe in fractions of a second. But Mars is not on our globe. Depending on the planet's alignment, a radio signal traveling at the speed of light takes between 4 and 24 minutes to cross the Gulf. This means a simple hello from a colonist on Mars would take, on average, 20 minutes to reach Earth, and the reply, "Hello, how are you?" would take another 20 minutes to return. This 40-minute round trip makes conversation impossible. It transforms all communication into a series of staggered messages, like letters or emails. There can be no quick calls for help, no casual real-time chats with family, no immediate guidance from mission control during a crisis. The colonists will be psychologically untethered, living in a time shadow, forced to become largely autonomous, their connection to home a stream of delayed voices from a world that is always irrevocably in the past. Areology is the specific name for the study of Martian geology. We are so accustomed to our own planet that our scientific language is built around it. Geology is, by its very root, the study of the Earth, or geo. But when we set foot on another world, our language must expand, adapting to a new alien context. Areology is the term that describes the geology of Mars, drawing its name from Ares, the Greek god of war, who is the counterpart to the Roman god Mars. It is a field of science that studies a planet of extremes, a world where the primary geological forces are not the same as ours. While Earth's story is dominated by plate tectonics and the sculpting power of liquid water, Mars's story is one of volcanic stillness, of catastrophic ancient floods, and of the slow, patient work of wind. An areologist is a planetary historian who reads the layers of dust in the polar caps, traces the towering cliffs of Valles Marineris, and chips at the hematite blueberries, all to understand the biography of a planet that took a profoundly different path from our own. The Great Filter is a chilling concept in astrobiology that Mars may help us understand. The universe is ancient and incomprehensibly vast, filled with trillions of planets. Statistically, it should be teeming with intelligent life. Yet when we listen to the cosmos, we hear only a profound, echoing silence. This is the Fermi paradox, and the Great Filter is one of its most sobering potential answers. It is the hypothesis that somewhere between the origin of simple life and the development of a galaxy-spanning civilization, there exists a barrier, a filter, that is extremely difficult for life to overcome. This filter could be the leap from single-celled to multi-celled organisms, the development of intelligence, or perhaps the challenge of surviving one's own technology, like nuclear war or climate change. Mars presents a crucial test. If we find fossils of simple life, but nothing more complex, it might suggest the filter lies in the leap to complexity or intelligence. But if we find Mars to be utterly, completely sterile, it might suggest that the emergence of life itself is the Great Filter. And if we, as a civilization, failed to successfully become a two-planet species by colonizing Mars, it might be a dark omen that the filter is still ahead of us. The first colonists would have to adapt to the psychology of a new sky, where Earth is just a pale blue dot. For all of human history, we have lived under a sky that is a protective blue dome, with a bright yellow sun and a large silver moon. This sky is our ceiling, our constant, our definition of up. On Mars, the sky itself would be a source of profound psychological dislocation. During the day, the thin atmosphere, filled with fine dust, scatters light differently, creating a faint, butterscotch pink or pale orange sky. The sun would appear smaller and weaker, a diminished source of light. At night, the sky would be a familiar, brilliant black, but the constellations would be subtly shifted, and two moons would race across the star field. But the most profound, and perhaps most isolating sight, would be Earth itself. Our home, with all its oceans, forests, history, and everyone we have ever known, would be reduced to a simple point of light, a bright bluish star in the evening. To see your entire world relegated to a single distant speck could be a source of transcendent awe or a trigger for a deep, quiet loneliness. The dark streaks on Martian slopes, known as recurring slope lineae, were once thought to be flowing briny water. For years, orbital images of Mars showed a tantalizing seasonal mystery. On the steep, sun-facing slopes of craters and canyons, dark, narrow streaks would appear during the warmest Martian months. They would grow and lengthen, flowing downhill like trickles of water, only to fade and disappear as winter approached. These recurring slope lineae, or RSLEs, were the subject of intense excitement, as they seemed to be direct, modern-day evidence of liquid water flowing on the surface. We imagined this water as a hyper-salty, antifreeze-like brine, melting in the faint warmth and creating potential microhabitats for life. However, more recent high-resolution analysis has provided a much drier and perhaps more mundane explanation. The current consensus is that these streaks are not an indication of water, but instead dry, granular flows like cascades of sand or dust. They are avalanches of fine-grained material set in motion by the thermal changes of the seasons. This is a story of science correcting itself, a reminder that on Mars, the simplest explanation, in this case, the ever-present dust, is often the one that holds true. The efficiency of solar panels is significantly reduced on Mars due to the planet's distance from the Sun and its dusty atmosphere. On Earth, solar power is a bright and powerful source of energy, with our panels soaking up the intense, direct light of a nearby sun under a relatively clear sky. On Mars, harvesting the sun's energy is a more delicate proposition. Mars orbits much farther from the sun than Earth, meaning the sunlight that reaches its surface is already about 40% weaker. Compounding this problem is the planet's ever-present fine red dust. This dust settles on everything, forming a thin, obscuring layer on solar panels that can block much of the light, requiring precious energy or robotic wipers just to keep them clean. And when the planet-encircling dust storms arrive, they can blot out the sun almost completely for weeks on end, plunging solar-powered colonies into a long, dim hibernation. This fragile reliance on a distant sun means that while solar power will be a component of Martian energy, it cannot be the only answer to surviving the long, cold night. The cold Martian nights, which last over 12 hours, will likely require colonists to use compact nuclear reactors for power. While solar panels can provide a vital source of energy during the long Martian day, they are useless when the pale sun dips below the horizon. As the planet plunges into the deep cold of its night, temperatures plummet, and the colony's life support systems, heaters, and experiments would all demand energy. The solution therefore, lies in the power of the atom. Small, compact nuclear reactors, like NASA's kilopower concept, are being designed for exactly this purpose. These are not the massive, complex power plants of Earth, but small, simple, and robust fission systems about the size of a refrigerator. They are designed to be buried in the regolith, safely shielded, and to passively generate a steady, reliable stream of electricity and heat for years on end, indifferent to dust storms, darkness, or cold. This constant, dependable heartbeat of power would be the essential lifeline, the electric hearth around which a new Martian home could be built. The design of a Martian spacesuit, like the Z2 prototype, must balance mobility with protection from a hostile environment. An Earth spacesuit, used on the International Space Station, is a marvel of engineering, but it is primarily a zero-gravity pressure vessel, a personal spacecraft. A Martian spacesuit has a far more complex job. It must be worn in a gravity field, meaning it must be lightweight and flexible enough for colonists to walk, bend, crouch, and perform geological work for hours on end. It must be, in essence, a wearable habitat. It must provide oxygen to breathe in a carbon dioxide world, maintain a comfortable temperature in a deeply cold environment, and shield the astronaut from solar and cosmic radiation. Perhaps its most difficult job, however, will be to fight the abrasive, incredibly fine Martian dust, which will try to clog its joints, scratch its visor, and breach its seals. Prototypes are exploring hard-shell torsos with suit ports on the back, allowing astronauts to dock with a rover or habitat and climb out of the suit, leaving the dusty, contaminated exterior safely outside. The true scent of Mars is unknown, but it would likely be sharp and metallic. We have never smelled another world directly, as our astronauts on the Moon were always in their suits, and our rovers have no sense of smell. But we have a clue from the Apollo missions. When the moonwalkers returned to their lunar module and removed their helmets, they were struck by a powerful, distinct scent from the grey dust that had clung to their suits. They described it as smelling like spent gunpowder or wet ash, a sharp, metallic, slightly burnt odour. Mars, being a world covered in fine iron oxide dust, would likely have its own unique, pervasive scent. If a colonist were to step inside after a long excursion, the regolith clinging to their suit would release a new aroma into the habitat's air. It would likely be metallic from the high iron content, perhaps slightly acrid from other minerals. It would be the smell of a sterile, ancient, volcanic world, the unmistakable perfume of a planet that is not our own. Thin, wispy clouds made of water ice and carbon dioxide ice are a common sight in the Martian sky. While Mars lacks the dense, dramatic, and rain-filled cloudscapes of Earth, its thin atmosphere is not without its own subtle, ethereal weather. High in the cold, thin sky, typically around the planet's equator during its winter, faint, ghostly clouds can be seen drifting. These are not the fluffy liquid water droplet clouds of our own world. Instead, they are composed of microscopic ice crystals. Some, the lower altitude clouds, are made of frozen water, like Earth's high altitude cirrus clouds. But others, forming even higher and colder, are made of frozen carbon dioxide, or dry ice, a phenomenon unique to Mars's frigid atmosphere. For a colonist on the surface, these clouds would be a faint, beautiful sight, catching the light of the setting sun and glowing in pale pinks and blues long after the surface has fallen into shadow, a delicate meteorological painting on a thin alien canvas. The primary scientific goal of colonization would be the search for past or present microbial life. The dream of finding life on Mars has driven our exploration for over a century, a question that sits at the very heart of our place in the universe. Mars today is hostile, but we know that billions of years ago, it was a world of rivers, lakes, and perhaps even oceans, possessing all the key ingredients for life as we know it: liquid water, organic compounds, and a source of energy. The first human colonists would not just be builders, they would be the ultimate explorers, equipped with sophisticated labs and the ability to travel to the most promising locations. They would drill deep beneath the surface, past the reach of sterilizing radiation, into layers of ancient ice or to the warm, dark aquifers where liquid water might still exist. They would search for fossils in the sediment of ancient riverbeds, or for the chemical signatures of microbes that might still be clinging to life deep underground. To be the one to find that, to confirm that life is not a miracle unique to Earth, would be one of the greatest discoveries in human history. The risk of fire in an oxygen-rich habitat is a constant, serious concern. On Earth, our atmosphere is a gentle, nitrogen-buffered mix, where only 21% is oxygen, making fire a manageable, though dangerous event. On Mars, our habitats, at least initially, may be filled with a higher concentration of oxygen at a lower pressure to make life support simpler and to reduce stress on the habitat structure. This enriched atmosphere, however, creates a highly flammable environment. In such air, a single spark, a frayed wire, or an overheated component could turn even a small ignition into a rapidly spreading fire. This was a lesson learned in the tragic Apollo 1 accident. For Martian colonists, fire safety is not a secondary concern. It is central. They must be vigilant, surrounded by fire suppression systems, and live in an environment where every material, every wire, and every action is chosen with the understanding that their home must remain safe in a world that cannot help put out a flame. The concept of planetary personhood is a legal and ethical idea that Mars should have rights, just as a person does. As we stand on the threshold of becoming a multiplanetary species, we are confronted with ancient philosophical questions in a new cosmic context. The idea of planetary personhood is a radical one, an extension of our expanding circle of empathy. It asks us to consider that Mars, even if it is sterile and lifeless, has an inherent right to exist as it is, a right to its own geological integrity and its own silent billion-year-old history. Proponents of this view, much like those who argue for a red Mars, suggest that to alter the planet, to mine it, to terraform it, or to pollute it without restraint is a violation. This framework challenges the very foundation of colonization, which is often based on the idea of human dominion over a resource. It forces us to ask, do we arrive on Mars as its owners, its stewards, or merely as its guests, bound by a profound respect for our ancient, silent host? The first human structures on Mars, the habitats and landers, will one day become protected historical sites. It is a strange thing to consider that the very act of landing and surviving will, in an instant, create the first human archaeology on another world. The landing site of the first crew, the base camp where the first habitat is inflated, the first footprints left in the red dust, and the first tools discarded will be the equivalent of our own Olduvai Gorge. These sites will be precious, marking the moment humanity's fragile bubble of life first established itself in a new ocean of existence. Future generations of Martian-born humans, perhaps living in a more developed world of cities and open air, will look back on these first tiny habitats with a profound, almost sacred reverence. They may preserve them, perhaps encasing them in protective domes, as monuments to the handful of people who crossed the great void in vessels of unimaginable fragility, carrying the seed of their civilization with them. The development of closed-loop life support systems is essential for long-term survival. On Earth, we live in a vast open-loop system, a planetary-scale biosphere that effortlessly recycles our water, scrubs our air, and decomposes our waste, a service so reliable we are rarely even conscious of it. On Mars, there is no such system. A colony must be its own tiny, perfect Earth, a hermetically sealed bubble where nothing important is wasted. This is the challenge of closed-loop life support. It means every drop of water must be reclaimed, not just from showers and sinks, but from the humidity of the air and the very urine of the crew, purified and returned to the drinking supply. It means every breath of exhaled carbon dioxide must be captured, fed to algae or chemical reactors, and split back into breathable oxygen. It means all biological waste must be processed, composted, and turned into nutrients for the hydroponic gardens. This is a task of subtle engineering, an attempt to create a miniature metabolism where the colony itself breathes, drinks, and digests in a continuous life-sustaining circle. The long-term effects of low gravity on the human immune system are largely unknown. Our bodies are intricate biological engines, calibrated over millions of years to the precise conditions of Earth's gravity, atmosphere, and microbial environment. When we move to Mars, into a world of 38% gravity and a sterile artificial habitat, we are beginning one of the largest, most uncontrolled experiments in human biology. Early data from astronauts on the International Space Station suggests that the immune system is affected by spaceflight, with some immune cells becoming less active and dormant viruses in the body reactivating. We do not yet know why, whether it is the lack of gravity, the stress, the radiation, or the sterile environment. On Mars, this could be a significant concern. A weakened immune system would make a crew more susceptible to infections that would be trivial on Earth. And in a tiny, enclosed habitat, a simple illness could spread to the entire crew. We must understand how our inner defenses, our very cells, perceive this new, lighter world. A gravity prescription might be necessary for colonists, using centrifuges to simulate Earth's gravity. The human body is a testament to the power of Earth's gravity. Our bones are dense, our muscles are strong, and our cardiovascular systems are tuned to pump blood against that constant downward pull. On Mars, in a world where everything is lighter, the body would interpret this as a signal to economize. It would begin to deconstruct itself, shedding bone density and muscle mass that it no longer perceives as necessary, a process that could be irreversible and limiting. To combat this biological surrender, colonists would likely need a gravity prescription. This would involve spending a portion of their day inside a human-sized centrifuge, a spinning device that uses artificial gravity to create a force that mimics the feel of Earth. They would have to, quite literally, spin themselves back to health, a gentle daily ritual to remind their bodies of the heavy terrestrial home they have left behind, ensuring they have the physical strength to live and work in the softer pull of Mars. The legal and ethical status of the first child born on Mars is a profound, unanswered question. Sooner or later, if a colony is to be truly self-sustaining, it will transition from a remote outpost to a true home, and that transition will be marked by the first human birth on another world. This single event will trigger a cascade of legal and philosophical questions for which we are utterly unprepared. What citizenship would this child hold? Would they be an American, a Chinese, or a Russian citizen, based on the nationality of their parents or the corporation that owns the habitat? Or would they be something new, the first Martian, a citizen of no earthly nation? What rights would they have, born into a hostile environment where a simple crack in a wall could be dangerous, and a return to Earth, with its crushing gravity, might be difficult or impossible for their low G-adapted body? This child would be the first true native of another world, a human born in a context our laws never foresaw, forcing us to redefine our most basic concepts of identity, nationhood, and home. The concept of a dying Earth narrative is a powerful and perhaps dangerous motivator for colonization. Much of the popular enthusiasm for colonizing Mars is underpinned by a deep-seated anxiety about our own planet. We see the narratives of climate change, resource depletion, and existential risk, and we look to Mars as a backup, a lifeboat, a plan B for humanity. While this is a powerful motivator, it is also a deeply flawed and perhaps distracting one. Mars is not a second Earth waiting to be claimed. It is one of the most hostile environments in the solar system, a frozen, irradiated, airless desert. The effort required to make even a tiny dome portion of Mars habitable for a handful of people is far greater than the effort required to address many of our problems here on Earth. If we frame Mars as an escape hatch, we risk indulging in a fantasy that draws attention away from our primary responsibility, which is to care for the one and only perfect, living cradle our species has ever known. The true value of Mars may not be as a replacement, but as a mirror, a place that, by its very harshness, teaches us to appreciate the miracle of our own blue world. The first colonies will likely be entirely dependent on Earth for complex manufactured goods for decades. We dream of Martian self-sufficiency, of bustling cities that are independent of their home world. But the reality is that the first colonies will be in a state of profound, fragile dependence. While colonists can learn to live off the land for basic survival, harvesting water, air, and building materials, they cannot replicate the high technology components that their lives depend on. They cannot fabricate microchips, advanced medical scanners, solar panels, or the complex engines of their rockets with ease. These items are the product of an Earth-spanning industrial web, a supply chain involving countless people and specialized factories. A habitat on Mars would be at the very end of the longest, thinnest, and most expensive supply chain in history. A single failed resupply mission from Earth could be serious, and this one-way flow of technology would define the relationship between the two worlds, making Mars less a fully independent nation and more a remote, high-tech research outpost for a very long time. Mars experiences seasons just like Earth, but they are twice as long. Our own seasons are a gentle, familiar rhythm, a 4-part cycle of growth, heat, harvest, and rest, all governed by the 23-degree tilt of Earth's axis. Mars too is a tilted planet, with an axial tilt of about 25 degrees, almost identical to our own. As it journeys around the Sun, this tilt means that it experiences the same cycle of spring, summer, autumn, and winter. But this is where the familiarity ends. Because the Martian year is almost twice as long as ours, each of these seasons is stretched out, lasting for 6 or 7 months. Furthermore, Mars's orbit is more elliptical or eccentric than Earth's, which makes the seasons uneven. The southern hemisphere experiences a short, relatively warm summer when Mars is closest to the Sun, and a long, cold winter when it is farthest away. This extended, lopsided rhythm would govern the lives of colonists, dictating when they can travel, when the dust storms are most likely, and when the faint sun will offer its weakest light. The search for methane in the Martian atmosphere is a hunt for a potential sign of life. On Earth, methane, a simple carbon-based gas, is overwhelmingly produced by living things, from the microbes in a cow's stomach to the decay in a swamp. It is a potent biosignature. For years, orbital probes and rovers have detected tantalizing transient plumes of methane in the Martian atmosphere, a gas that shouldn't be there in such quantities. The sun's ultraviolet light should break down any methane in the thin air within a few hundred years, so its continued presence implies that something, somewhere, is actively replenishing it. This has created two competing and equally fascinating explanations. The first, the biological one, is that this methane is the exhalation of living, methanogenic microbes deep underground, huddling in warmer, wetter niches. The second, the geological one, is that the methane is the product of serpentinization, a chemical reaction between water and certain minerals in the rock. The race is on to pinpoint the source of these plumes, a scientific detective story where the answer will tell us if Mars is geologically active or just perhaps biologically alive. Robotic precursors, like the Mars Sample Return mission, are critical to paving the way for human colonists. Before we send human beings on the perilous, multi-year journey to Mars, we must first let our robotic emissaries do the hard, preparatory work. Humans are fragile, requiring massive, complex life support systems, but robots are hardy, patient, and expendable. The Mars Sample Return mission, a complex, multi-launch campaign, is the embodiment of this philosophy. It involves one rover to drill and cache the most interesting rock samples, a second lander to retrieve those samples and launch them into Mars orbit, and a third spacecraft to catch that orbital package and fly it back to Earth. This mission is not just for science. It is a full-scale rehearsal for the technologies of colonization. It will refine the art of landing heavy payloads, of launching a rocket from another planet's surface, and of making the long journey home. Our robotic children are, in essence, building the infrastructure and writing the safety manuals for the first human footsteps that will follow them. The discovery of subterranean lakes of liquid water, like the one suspected beneath the southern ice cap, has changed our view of Mars. For decades, we believed the only water on Mars was frozen solid or a wisp of vapor, with the planet's surface conditions making liquid water an impossibility. But in recent years, radar-sounding instruments orbiting the planet have peered deep beneath the southern polar ice cap, using radio waves to paint a picture of the world below the ice. There, more than a kilometer down, they detected a bright, reflective patch, an anomaly that strongly suggests a large, stable body of liquid water, a subterranean lake. This water is likely kept liquid, not by warmth alone, but by the insulating pressure of the ice above and by a heavy concentration of salts, which act as a powerful antifreeze. This discovery is world-changing. It means that Mars today possesses one of the most important ingredients for life, hidden away in the dark, a cold, salty, and ancient reservoir that would be an immensely compelling target for future explorers. The concept of a Dyson swarm around Mars is a far-future terraforming idea. When we speak of warming Mars, we often think of releasing greenhouse gases or building giant mirrors in orbit, but these are modest proposals compared to the grand theoretical engines of advanced civilizations. A Dyson swarm, a variation of the Dyson sphere, is a megastructure proposed by futurists. It would consist of a vast cloud of countless independent solar-powered satellites, or statids, orbiting the Sun. These satellites would not be orbiting Mars itself, but would be positioned to collect a tremendous amount of solar energy and beam it, perhaps as microwaves or lasers, directly onto the Martian surface. This would be a focused, persistent stream of energy, an artificial sun dedicated to a single task, melting the polar ice caps, releasing the frozen carbon dioxide, and initiating a runaway greenhouse effect. This is a vision of terraforming, not as a gentle biological process, but as an act of large-scale astronomical engineering, a project more like a thought experiment than a near-term plan. The Mars Curse, or the Great Galactic Ghoul, is a term for the historically high failure rate of Mars missions. Mars, our closest and most tantalizing planetary neighbor, has also been our most challenging. Since the 1960s, humanity has launched over 50 robotic missions toward the Red Planet, and for a long, frustrating period, more than half of them failed. Some missed the planet entirely, some burned up in its atmosphere, some crashed on its surface, and some simply vanished, their signals falling silent in the deep void. This string of failures, especially early on, led engineers to half-joke about a great galactic ghoul existing in the space between Earth and Mars, a creature that feeds on ambitious probes. In truth, this curse was simply a testament to the profound difficulty of interplanetary travel. The tiny launch windows, the long-duration voyages, the complex orbital insertions, and the 7 minutes of terror landing sequence present 1,000 points of failure. The curse is lifting now, as our technology improves, but it remains a sobering reminder of the humility required to cross the void. The Aryan calendar, proposed by aerospace engineer Thomas Gangale, is a detailed attempt to create a functional Martian calendar. The simple fact of a roughly 668 Sol Martian year creates a logistical challenge for a new society. How do you divide this long year? How do you name the months? How do you keep the days aligned with the seasons? The Aryan calendar is one of the most thorough proposals, a beautiful piece of speculative timekeeping. It divides the long Martian year into 24 months, each named for a different constellation of the zodiac, alternating between a Greek and a Sanskrit name. Each month has either 27 or 28 sols. The calendar also designates the Martian equivalent of a leap sol and establishes a new epoch or year zero based on the first successful robotic landings. To adopt such a calendar would be a profound cultural step, a moment when colonists officially abandon the timekeeping of their home world and begin to mark their lives by the turning of their new one. The psychological need for biophilia, the love of life and living systems, will be critical for colonists. Humans evolved in a green, blue, and brown world, a rich biosphere filled with the sights, sounds, and smells of other living things. The rustle of leaves, the scent of rain, the song of a bird. We have a deep, instinctive need to be near life, a concept known as biophilia. On Mars, colonists will live in a world that is the opposite. A sterile, silent, dead, red environment encased in metal and plastic. The psychological pressure of this profound life sickness could be immense, leading to sadness or a sense of emptiness. To combat this, habitats will not just be functional, they must be beautiful. They will need to incorporate bright, sunlit greenhouses, not just for food, but for the simple, morale-boosting joy of seeing something green. They will need parks, fountains, and perhaps even small animals, all in an intentional attempt to replicate the simple, vital comforts of the living biosphere. They left tens of millions of kilometers away. The energy required to return from Mars to Earth is a major logistical challenge. A one-way trip to Mars, while difficult, is a journey of falling down a gravity well and coasting. The return journey is an entirely different and much harder proposition. To get home, colonists must first escape Mars's own gravity, which requires a rocket. This means the colonists must not only land their habitat, their life support, and themselves, but also an entire ascent vehicle, the Mars Ascent Vehicle. This vehicle must be robust enough to sit on the surface for over a year, waiting for the return window. The fuel for this rocket is the single heaviest item in the entire mission architecture. This is why ISRU, the ability to manufacture rocket fuel, methane and liquid oxygen, from the Martian water and atmosphere, is not just helpful, it is central. Without it, the mass of the fuel we would have to land on Mars becomes so large that the entire mission strains the limits of current technology. A lava tube skylight, or a collapsed pit in a lava tube, is a prime target for exploration and colonization. The discovery of subterranean lava tubes was a theoretical breakthrough, but it presents a new problem. How do you get inside them? They are, by definition, underground. The answer, it turns out, is written on the surface. Orbital images of volcanic regions on Mars have revealed dozens of strange, perfectly circular, deep pits, holes in the ground that are not impact craters. These are skylights, sections of a lava tube ceiling that have collapsed under their own weight, creating a natural entrance into the vast cavern system below. These skylights are some of the most exciting targets on the entire planet. They are doorways. A mission could land nearby, send a rover or, one day, a human crew down into the opening and gain access to a protected, radiation-free environment that has been sealed off from the surface, perhaps for billions of years. These dark, silent caves are not just potential homes. They are time capsules, pristine environments where the secrets of Mars's past might be waiting in the dust. The legal concept of who owns Mars is fundamentally unsettled and will be defined by the first colonists. While the 1967 Outer Space Treaty forbids nations from claiming sovereignty, it was written before the rise of private aerospace, before companies declared their intention to build cities on Mars. This creates a vast legal grey area. If a private corporation, not a nation, funds and builds the first self-sustaining colony, what laws apply? Does the company own the land it builds on? Can it claim exclusive rights to the water ice in a specific crater? What authority governs the colonists who live there? The laws of the company, the laws of the nation the company is registered in, or a new self-drafted Martian charter? The first people to live and work on Mars will not just be pioneers, they will be precedents, the test cases for an entirely new branch of human law. The true law of Mars will not be written only in treaties, but in the practical reality of who gets there first and how they choose to live. The Martian sunset appears as a serene, dusty blue. We are creatures of a blue sky planet, and our art, our poetry, and our sense of home are tied to the warm, fiery colors of our sunset, the reds, oranges, and pinks that paint our evening sky. This spectacle is the result of light scattering through our nitrogen-rich atmosphere, a process called Rayleigh scattering. On Mars, the physics of the sky are different. The atmosphere is thin, but it is filled with fine reddish dust. During the day, this dust scatters the red light, which is why the sky itself appears a pale, pinkish orange. But as the small, distant sun sinks toward the horizon, the light must travel through even more of this thin, dusty air. The red light is scattered away, and it is the blue wavelengths that penetrate most effectively, creating a soft, ethereal, and cool blue aura that lingers around the setting sun, a reverse of our own familiar experience. A colonist would end their long soul by watching this quiet, blue fire, a moment of beauty that is both alien and profoundly peaceful. The abrasive, electrostatically charged Martian dust is a critical engineering threat. We think of dust on Earth as a simple nuisance, a layer of grime to be wiped away. But the dust on Mars, the regolith, is a different and more troublesome substance. It is not the soft, organic detritus of our world, but a fine talcum powder-like particulate of volcanic rock, rich in iron, silica, and other abrasive minerals. It is also, in the thin, dry air, charged with static electricity, causing it to cling to everything: visors, seals, solar panels, and moving parts. The Apollo astronauts on the moon discovered the danger of such dust. It was sharp, like microscopic shards of glass, and it tore at their suits, clogged their zippers, and irritated their lungs. The Martian dust will be a relentless, pervasive foe, a quiet antagonist that will seek to sandblast, jam, and wear down the colony's technology. We must invent new ways to mitigate it, perhaps by creating mud rooms with air showers, or by designing systems that are never directly exposed to the outside. Managing the dust well will be essential to the colony's long-term health. The soundscape of Mars, first recorded by the Perseverance rover, is a profound, windswept silence. We live on a planet that is never truly quiet, a world teeming with the noise of life and motion, the hum of insects, the rush of water, the sigh of wind through trees, the distant rumble of our own civilization. We had to imagine what Mars sounded like until the Perseverance rover, carrying 2 small microphones, landed in Jezero crater. What it recorded was the sound of near desolation. The dominant noise is the wind, a thin, ghostly whisper, a high-pitched sigh as the wispy carbon dioxide atmosphere moves across the sand. Because the air is so thin, sounds do not carry well. They are muffled, faint, and close. A colonist would live in a world of almost total exterior silence, a place where their own habitat would be the only persistent source of noise. To step outside would be to be enveloped in a quiet so deep and so ancient that the only other sounds would be the creaks of their own suit and the soft crunch of their boots on the gravel. The Viking 1 lander's labeled release experiment in 1976 produced ambiguous, still debated results about life on Mars. In the summer of 1976, 2 robotic landers, the Vikings, touched down on the Red Plains. carrying a suite of experiments designed to answer a single great question. Are we alone? One of these, the labeled release experiment, was an ingenious chemical test. It took a sample of Martian soil, dampened it with a broth of nutrients that had been tagged with radioactive carbon, and then waited. The hypothesis was that if microbes were in the soil, they would eat the nutrients and exhale the radioactive carbon as a gas, which the lander's sensors would detect. The experiment worked. The gas was released, and the graphs in the mission control spiked, a result that, on Earth, would have been a strong positive for life. And yet, a partner experiment, designed to find the organic bodies of these microbes, found nothing. This great contradiction has haunted science for decades. Was it a chemical quirk of the strange Martian soil, the perch laureates reacting with the nutrients? Or did we, in our very first attempt, briefly interact with a living alien ecosystem, only to dismiss its breath as a chemical anomaly? Advanced artificial intelligence will be a mandatory co-pilot for the first Martian colonists. On Earth, a crisis is managed with the support of a global network of experts, a mission control that can provide real-time data and guidance. On Mars, the 20-minute light speed delay makes this impossible. A colonist facing a sudden habitat leak, a medical emergency, or a life support failure will be, in that moment, entirely on their own. Their survival will depend not just on their own training, but on the digital mind living in their habitat's computers. This AI will be more than a tool. It will be a crew member. It will be an autonomous mission controller, a diagnostician, a doctor, and a systems engineer all at once. It will have to monitor thousands of life support variables simultaneously, predict cascading failures before they happen, and provide the crew with immediate, clear, and calm guidance for problems no one has faced before. This silicon partner will be the unseen vigilant guardian of the colony, a mind that never sleeps and that holds the complex blueprint of survival in its memory. The concept of a Martian constitution explores the need for a new social contract for a new society. When colonists leave Earth, they are not just moving to a new location. They are, in a very real sense, moving to a new kind of existence. They will be living in a world where the fragility of life is a daily reality, where a single mistake can endanger the entire community, and where the old laws of Earth, forged in a world of open air and abundant resources, may not neatly apply. This has led philosophers and legal scholars to draft speculative Martian constitutions, attempts to think through the new principles this society might need. How will power be shared when the habitat commander also controls the oxygen supply? What does freedom mean in a world where going outside unprotected is impossible? How will resources be allocated when everything is scarce? The first colony will be a political and ethical testbed, a chance to see if, on a new world, we can build a society that is more resilient and perhaps more cooperative than the one we left behind. The first human colonies will almost certainly involve major private corporate ventures, not only national government-led ones. For most of the 20th century, space exploration was the sole domain of superpowers, a grand geopolitical display of national pride and technological might, funded by taxpayers. But the economics of the 21st century are different. The immense, multi-decade cost of establishing a permanent, self-sustaining presence on Mars is a burden that few, if any, governments are eager to shoulder alone. Instead, the momentum has shifted to the private sector, to companies and visionary leaders who see Mars not as a political prize, but as the next great frontier for human expansion, a long-term commercial investment, or even a philosophical necessity. This means the first Martian settlement may feel as much like a company town as a flag-bearing colony. This changes the nature of the endeavor, shifting some of its goals from pure science and prestige to survival, growth, and eventually, perhaps, an interplanetary economy. The psychological profile of a one-way colonist is a subject of intense speculation and study. To migrate to Mars, especially in the first few decades, will not be like a posting in Antarctica, a difficult journey with a guaranteed return ticket. It will be, for many, a one-way trip, a permanent commitment to a new world. The colonists who sign up for this will be a self-selecting, unusual subset of humanity. They will be people who are willing to leave behind everything: their families, their culture, the biosphere of Earth, the feeling of rain, and the sight of an open ocean, possibly forever. What motivates such a person? Is it a profound sense of historical purpose, a desire to be the Mayflower generation of a new civilization? Is it a deep dissatisfaction with the world of Earth? Or is it a personality uniquely suited to isolation, high-stakes problem-solving, and a complete dedication to a future they are building but may not live to see fully realized? They will be, in essence, our first generation of intentional exiles. The development of an interplanetary internet is complicated by the speed of light, requiring a store and forward system. We have woven our world together with a web of near-instant communication, a network that allows us to stream video and have conversations in real time. This system, the internet, relies on the assumption of a continuous, low-latency connection. But in an interplanetary solar system, this assumption breaks down. The vast distances mean that light itself, the fastest thing in the universe, takes minutes to cross the void, making a live connection impossible. To solve this, engineers are building a new protocol, a delay-tolerant network. This is an internet built on patience. Data will not be streamed. It will be sent in robust bundles, which will hop from a satellite orbiting Earth to a relay station in deep space, to a satellite orbiting Mars, where it will be stored and only then forwarded down to the colonist. It is a system of celestial data buckets, a new web where every message must quietly wait its turn, accepting the fundamental unchangeable speed limit of the cosmos. Cryosleep, or induced human torpor, is a potential technology for mitigating the hazards of the long journey to Mars. The 7 to 9 month voyage through interplanetary space is not just a test of patience. It is a period of real biological risk. The crew is exposed to cosmic radiation, the bone-wasting effects of zero gravity, and the psychological strain of confinement. One proposed, though still speculative, solution is to have the crew not be fully awake for the journey at all. This is the concept of torpor, a medically induced hibernation. By slowing the human metabolism, lowering body temperature, and reducing consciousness to a low-level hum, we could potentially protect them. A sleeping body may be less susceptible to certain kinds of damage. Its muscles and bones might atrophy less, and the psychological burden of the 9-month confinement would simply pass like a single long night. This would change the nature of the mission from a long endurance test into a quiet passage. The first agricultural crop successfully grown in simulated Martian soil is the humble potato. When we imagine the first farms on Mars, we must first consider the profound challenges: the toxic soil, the low light, and the need for efficiency. The potato, a crop we often take for granted, has emerged as a likely pioneer. In experiments here on Earth, using simulated regolith developed by NASA and added nutrients, scientists have successfully grown potatoes in these harsh, salty conditions. The potato is a nutritional powerhouse. It is dense in calories, rich in vitamin C and potassium, and it grows underground, protecting its edible portion from surface radiation. It is resilient, efficient, and, once the perchlorites are washed from the soil, remarkably tolerant. The first human-tended farm on Mars will likely not be a field of wheat, but a small, humble patch of potatoes, a Martian root vegetable providing the first, essential, and comforting calories for the colonists. The sheer logistical challenge of packing spare parts for a Mars colony makes advanced 3D printing a non-negotiable essential technology. On Earth, if a critical piece of equipment breaks, a new part can be ordered and delivered quickly from a vast global supply chain. On Mars, that same supply chain is millions of miles long, and a new part is, at best, many months away. This is an unacceptable vulnerability. A colony cannot survive if it is dependent on a spare parts closet that is on another planet. The solution is to bring the factory with you. This is the promise of advanced 3D printing, or additive manufacturing. Colonists will not bring 1,000 different screws, brackets, and tools. They will bring 3D printers and large supplies of raw feedstock, such as metal powders, polymers, and ceramics. When a part breaks, they will not order it. They will print it. When they need a new specialized tool, they will design it and fabricate it on site. This technology is key to true self-sufficiency, transforming the colony from a fragile outpost into a more independent, adaptable base. Martian resource prospecting will use orbital radar and spectrometers to create a treasure map for colonists. Before the first settlers can truly live off the land, they must first know where the land holds its most precious resources. Mars, from the surface, can look like a homogeneous dusty desert, but from orbit, it is a world of incredible chemical diversity. Specialized spacecraft will act as prospectors, using advanced instruments to create maps for future settlers. Ground-penetrating radar will peer deep beneath the dust, searching for the telltale shimmer of buried water ice, or the hollow, dark shapes of lava tubes. Spectrometers, which analyze the colors of light reflected from the surface, will create detailed chemical maps, highlighting the locations of valuable minerals, metallic ores, and, perhaps most importantly, hydrated clays that signal regions once rich in water and now prime targets in the search for ancient life. These maps will be the first colony's blueprints, dictating where they can land, where they can drink, and where they can build. The first generation of Martian colonists will have to develop a unique wilderness survival mentality. We often think of astronauts as highly trained, sterile, technical operators, living inside pristine, white-walled laboratories. But the first Mars colonists will be something else entirely. They will be more akin to Arctic explorers or frontier pioneers. They will be living in a world that is not just indifferent to them, but actively, passively trying to end their mission every second. Their lives will be a daily, hands-on interaction with a lethal environment. They must be more than scientists. They must be master plumbers, mechanics, electricians, and farmers. They must be able to patch a leaking habitat wall with improvised materials, repair a critical life support rover with limited tools, and diagnose their own medical emergencies. This is a new kind of blue-collar astronaut, a frontier person who combines the mind of a researcher with the hands of a master carpenter, and who possesses a calm resilience in the face of constant quiet risk. The strange orbits of Phobos and Deimos mean they can both be visible in the Martian sky at the same time. A colonist looking up at the night sky would see a celestial dance unlike anything visible from Earth. Our own moon is a solitary, majestic presence, rising and setting in a slow, predictable cycle. Mars, with its 2 captured, lumpy moons, provides a more chaotic and dynamic show. Phobos, the inner moon, is so close that it whips around the planet in less than 8 hours, faster than Mars rotates. It rises in the west, a fast-moving point of light, and sets in the east only a few hours later, and it can do this twice in a single sol. Deimos, farther out, moves more slowly, a tiny, bright speck that can linger in the sky for 2 sols at a time. This means there are frequent, beautiful moments when a colonist could see both moons at once, one racing one way, the other drifting slowly in another, a constant, silent reminder of the planet's gentle gravitational embrace. The thin atmosphere of Mars is cold enough to have snow made of carbon dioxide. We think of snow as a soft, gentle, and comforting precipitation, the frozen form of the water that gives us life. On Mars, the atmosphere is so frigid, especially during the long, dark polar winters, that the planet experiences a different and far more alien kind of snow. The atmosphere itself, made largely of carbon dioxide, freezes solid and falls. This is not the fluffy, 6-sided water ice crystals of Earth, but a fine, grainy, dry ice snow. Orbital probes have watched as this carbon dioxide frost blankets the polar regions every winter, building up a seasonal ice cap several meters thick. This is a weather phenomenon of profound strangeness, a world where the very air becomes a solid, a landscape where the sky itself falls, not as life-giving water, but as the frozen breath of a cold, thin atmosphere. The Martian magnetic field is not a global shield, but a series of localized, fossil magnetic patches. Billions of years ago, Mars was a warmer, wetter planet, and it was protected by a powerful, global magnetic field, just like Earth's. But as the planet's small core cooled and solidified, this dynamo died, and the solar wind stripped the planet of much of its atmosphere and protection. However, the story does not end there. That ancient magnetic field left behind ghosts in the crust. In the southern hemisphere, orbital magnetometers have discovered patches of rock that are still intensely magnetized, like compass needles frozen in time. These are fossil fields, regions where the molten, iron-rich rock solidified and remembered the direction of the magnetic field from billions of years ago. These patches are not large enough to protect the whole planet, but they do create small, local magnetic umbrellas, regions of the surface that are more shielded from radiation than others. These magnetic oases could be prime landing sites, where the planet's own ancient memory offers a small but welcome pocket of shelter. The D in the spacesuit acronym NDX-1 stands for dust, signifying its primary design challenge. When the University of North Dakota set out to design a spacesuit specifically for planetary exploration, they focused on the single greatest lesson learned from the Apollo missions: the profound, persistent power of dust. The resulting suit, the NDX-1, is a prototype where the D in its name explicitly calls out its purpose. This suit is an armored, dust-resistant design It uses protective flaps to cover every joint, bearing, and zipper, preventing the abrasive, fine particles from getting in. It explores hard, smooth outer surfaces that are easier to wipe clean, and a rear entry suit port design, which would allow an astronaut to leave the dusty, contaminated suit attached outside the habitat, like a pair of boots left on the porch. The very name of this suit is a statement of humility, an acknowledgement that one of the greatest enemies on Mars may not be the dramatic hazards we imagine, but the simple, relentless, and microscopic grit that covers everything. The red color of Mars is a form of deep planetary scale rust. We see Mars in the night sky as the red planet, a fiery amber point of light. This color, which ancient cultures associated with war and blood, is in fact the signature of a slow, planet-wide chemical transformation, an event of ancient oxidation. The surface of Mars is incredibly rich in iron, a legacy of its volcanic past. Billions of years ago, when the planet's atmosphere was thicker and perhaps held more oxygen, or when water and other chemical agents were more active, this iron in the soil and rocks began to rust. It combined with oxygen to form iron oxides, like hematite, the same chemical process that causes a nail to turn red and crumble in the rain. Mars is, therefore, a world that has been slowly, pervasively rusting for eons, its surface covered in a fine reddish dust that is the remnant of its more dynamic and perhaps wetter past. Its color is not a sign of fire, but of a cold, slow, and ancient change. The long-term health of colonists will depend on their ability to manufacture their own pharmaceuticals on Mars. We take for granted the vast planetary scale pharmaceutical industry of Earth, a network that produces, tests, and delivers countless complex medicines to us with astonishing speed. But on Mars, this supply chain is severed. A colonist cannot simply go to a pharmacy for an antibiotic, a painkiller, or a life-saving medication. Furthermore, the medicines that are brought from Earth, even in the most carefully shielded containers, will be under constant assault from cosmic radiation, which can slowly break down their complex chemical structures, reducing their potency and shelf life. The solution is for the colony to become its own pharmacy. This will likely require small-scale automated chemical synthesizers, molecular 3D printers that can, given the right raw ingredients, build these life-saving drugs on demand. It may also involve farming, the genetic engineering of plants in the hydroponic bays to produce specific proteins and medicines, turning a simple leaf into a therapeutic agent, a quiet, green form of molecular alchemy. Future Martian rovers used by human explorers will need to be pressurized, mobile habitats. The robotic rovers we have sent so far, like Spirit, Opportunity, and Perseverance, are incredible, goat-sized geologists, but they are merely our remote-controlled eyes, tools driven from the safety of another planet. When humans arrive, their exploration needs will be profoundly different. They cannot be constrained to short walks around their habitat. They must be able to cross the vast alien landscapes for days or weeks at a time. This requires a new class of vehicle, the pressurized rover. This will not be an open-air buggy, but a small, mobile habitat, a combination of truck, lab, and camper. Colonists will live inside it in shirt sleeves, driving across the plains without their spacesuits, only docking at the back to step outside for geological work. These rovers will be their lifeboats, their laboratories, and their homes on the road, the covered wagons of the Martian frontier, allowing them to truly explore the silent wilderness beyond their landing site. The third quarter phenomenon is a recognized psychological pattern for isolated crews. In the cold, confined, and unchanging environments of Antarctic research stations and submarines, psychologists have observed a curious and consistent rhythm. The first quarter of a mission is a time of excitement, adaptation, and novelty. The second quarter is one of steady, productive work. But the third quarter, the period after the halfway point, when the end is not yet in sight, is often the time of greatest psychological strain. This is when morale can dip, when conflicts between crew members flare more easily, and when apathy or frustration can set in. It is the long middle of the journey, where the crew feels most isolated and routine begins to feel like a cage. On Mars, where a mission might last for years or even a lifetime, this phenomenon is a real concern. A Mars colony social structure must be built with this in mind, with careful attention to mental health, meaningful work, and supportive relationships, recognizing that the greatest challenge may not be the environment, but the slow, predictable passage of time itself. Extracting the abundant water ice from the Martian soil will be a difficult, energy-intensive process. We know that just beneath the dust, especially at the mid-latitudes, Mars is covered in a vast permafrost of water ice, a frozen reservoir that holds much of the planet's future potential. But this ice is not a clear, harvestable block like an ice cube. It is mixed intimately with the soil, frozen as hard as cement. To get the water out, colonists cannot simply dig it up and melt it. They must become vapor miners. This will likely involve large, autonomous machines that crawl the surface, scoop up the frozen soil, and place it in sealed, heated chambers. By baking the regolith, they will cause the water ice to sublimate, turning directly into steam. This steam will then be captured, condensed, and collected, one careful drop at a time, leaving behind a pile of dry dust. This is an industrial process, a form of planetary-scale mining for water, and it will be one of the most energy-intensive but most essential tasks in the early colony. The entire planet of Mars is covered in a global layer of fine dust, a homogeneous blanket that conceals the geology beneath. On Earth, our landscapes are diverse, a patchwork of bare rock, deep oceans, green forests, and icy poles, all shaped and cleaned by the constant, dynamic action of liquid water. On Mars, the dominant geological force for the last billion years has been the wind, and its primary action has been to move dust. This fine iron oxide powder, the rust of the planet, has been lifted, carried, and deposited by the thin atmosphere until it has covered nearly everything. From the deepest canyons to the highest volcanic peaks, almost every surface is draped in this soft, reddish-brown blanket. This makes the job of an areologist challenging, as they are often looking not at the true rock of the planet, but at its dusty sedimentary veil. To understand Mars, we must learn to see through this covering, to drill beneath it, or to find the rare, wind-scoured places where the planet's true, ancient, rocky bones are exposed. The first instance of a serious crime on Mars will be a profound test of the colony's and Earth's legal framework. We go to Mars with our highest ideals as scientists, explorers, and pioneers. But we will also go as human beings, carrying all of our flaws, our tempers, and our capacity for conflict, in a small, pressurized habitat where every person's life depends on the actions of everyone else. a simple argument could be disruptive, and a true crime, a theft, an assault, or deliberate sabotage would be a crisis. Who would have jurisdiction? Would Earth's laws, thousands of miles and many minutes away, apply directly? Who would be the police, the judge, and the jury? And what would be a fair punishment in a world where a prison cell is a scarce resource? An exile into the outside environment is not a humane option. The first Martian crime will not just be a personal tragedy, it will be a small constitutional crisis, forcing a tiny, isolated society to define its own system of justice in the most unforgiving environment imaginable. A vast buried tundra of glacial ice has been discovered in the Martian mid-latitudes, a resource that changes everything. When we thought of Martian water in the past, we used to look to the poles, the most obvious, but most difficult and coldest places to build a colony. But in recent years, orbital radar has revealed a stunning secret hidden beneath the dusty plains of the mid-latitudes, the more temperate and Earth-like regions of the planet. Here, in places like Arcadia Planitia, there are vast, buried sheets of water ice, some as large as US states and as thick as city skyscrapers. This is not just permafrost. It is, in essence, a buried glacier, a remnant of a past ice age protected from evaporation by a thin, insulating blanket of dust. This discovery has rewritten the map of colonization. The best place to land, the best place to build, may not be the most scenic canyon, but the place that sits directly on top of this massive, accessible, life-giving ice. The first Martian cities may be built not on exposed rock, but on their own hidden frozen reservoir. The discovery of fossilized life on Mars would present a profound ethical dilemma for terraforming. We go to Mars with two powerful desires: the search for life and the dream of creating a new home. The discovery of simple, fossilized microbes in an ancient riverbed would be one of the greatest scientific achievements in history, a confirmation that life is not unique to Earth. But what if, in that same soil, we find not just fossils, but dormant, sleeping microbes, life that is not dead, but simply waiting? This discovery would trigger a deep ethical question. Do we proceed with our dream of terraforming? Do we warm the planet, melt the ice, and thicken the air, knowing that this more Earth-like environment might be deeply harmful to any native, anaerobic Martian life? Do we have the right to ignite a new biosphere if it means overwhelming the only other life we have ever known? The first fossil would force us to choose how we balance our impulse to create with our duty to protect. The Martian poles in spring are home to dark fans, the explosive geysers of carbon dioxide. The seasonal rhythm of the Martian poles is a process of alien and striking beauty. During the long, dark winter, the carbon dioxide atmosphere freezes, building a deep, translucent slab of dry ice over the polar caps. When the first faint light of spring arrives, the sunlight passes through this translucent ice and warms the dark ground beneath. This dark ground heats up, and the dry ice in contact with it sublimates, turning directly into a high-pressure gas. This trapped gas, seeking an escape, eventually builds up enough pressure to rupture the ice slab above in a sudden event. A burst of carbon dioxide gas erupts into the thin air, carrying with it a plume of dark sand and dust from beneath the ice. This dark material then settles back on top of the ice in the direction of the wind, creating the beautiful, dark, fan-shaped patterns that orbital probes see every spring. This is the weather of Mars, a seasonal cycle of ice, light, and short-lived, gentle explosions of gas and dust. The long-term economic model for a Mars colony is a mystery, likely based on data, patents, or scarce resources. The initial exploration of Mars is a task of immense, almost incomprehensible expense, funded by governments or private fortunes for reasons of science, prestige, or vision. But for a colony to be truly self-sustaining, it cannot remain a permanent charity project. It must, eventually, have an economy. It must produce something so valuable that Earth is willing to pay the astronomical shipping costs to obtain it. What could this be? It is unlikely to be bulk materials like iron, which we have in abundance here. It could be intellectual property, the patents and technologies invented by a high-tech colony forced to innovate in isolation. It could be unique data and scientific discoveries from another world. Or it could be something we have not yet imagined. Perhaps the harvesting of rare isotopes, or the mining of asteroids using Mars as a staging ground. The first colony will be not just a new society, but the first test of a truly interplanetary economic idea. Algae bioreactors will be a vital multi-purpose life support system for a Martian colony. In the confined, resource-poor environment of a habitat, every system must perform multiple duties. The humble algae, one of Earth's simplest and most ancient life forms, is a perfect candidate. A colony may be filled with glowing, green, bubbling tanks of algae, bioreactors that are the living, breathing heart of the life support system. These algae will be voracious consumers of carbon dioxide, constantly scrubbing the air of the crew's exhalations and, through photosynthesis, producing a steady supply of fresh, breathable oxygen. But their work does not end there. Algae are also nutrient-dense and fast-growing. They can be harvested, processed, and turned into a protein-rich, if not very glamorous, food supplement. And finally, specialized strains can help process the colony's wastewater, consuming nitrates and phosphates, thus closing the loop on water, air, and food. A quiet, green engine that ties the habitat together. A sudden, unpredicted solar flare poses one of the greatest radiation dangers to colonists. While we plan for the constant, low-level drizzle of galactic cosmic rays by burying habitats and using shielding, there is a more intense, sudden, and unpredictable threat: the Sun itself. Our Sun is a dynamic star. It can, with little warning, unleash a solar particle event, a burst that flings billions of high-energy protons into space at high speed. On Earth, our magnetic field and thick atmosphere protect us from the worst of this. An unshielded astronaut in deep space, or on the surface of Mars, would have limited time to get to safety if such an event occurred. The radiation dose from a strong event could be dangerous. This means every habitat, rover, and base must be part of a space weather alert system. Colonists must have designated storm shelters, perhaps heavily shielded rooms surrounded by water or other protective materials, where they can retreat and wait for the Sun's brief, energetic outburst to pass. The lack of plate tectonics on Mars is the reason its volcanoes are so unimaginably large. Earth is a geologically dynamic, restless planet. Its crust is broken into a mosaic of plates that are constantly shifting, crashing together to form mountains and sliding over hotspots in the mantle. This is why our own volcanoes, like the Hawaiian Islands, form in chains as the crust moves over a stationary plume of magma. Mars, however, is a one-plate planet. Its crust is a single solid shell, and it has been for billions of years. This means that when a magma plume, a hotspot, formed deep in its mantle, it stayed in one place, and the crust above it stayed in one place as well. For a billion years, this plume patiently, steadily poured lava onto the same region, building a single, monolithic, titanic structure. Olympus Mons is the result of this profound stillness, a volcano that was allowed to grow layer by layer for an epoch of geological time, a monument to a planet's lack of motion. Humanity already possesses and has studied pieces of Mars right here on Earth. While we have spent billions sending robotic rovers to analyze Martian rocks, a strange cosmic delivery service has been sending us free samples for ages. We have found over 200 Martian meteorites, rocks that were blasted off the surface of Mars by ancient, massive impacts. These fragments of the red planet drifted through space for millions of years, their orbits eventually crossing paths with Earth, until they were captured by our gravity and fell to the ground, most often preserved in the icy deserts of Antarctica. By analyzing the trapped gases in these rocks, we can match their atmosphere to the one the Viking landers measured on Mars, confirming their origin. These cosmic messengers are a gift. They are real, physical pieces of another world, a tangible connection that has allowed us to study Mars's chemistry, its age, and its ancient magnetic field, long before we ever dreamed of sending a rocket to retrieve a sample ourselves. The extremely low atmospheric pressure on Mars means that human exposure without a suit would be quickly fatal. We often focus on the cold and the lack of oxygen when we speak of Mars's hazards, but the most immediate threat is the pressure. On Earth, we live at the bottom of a deep, heavy ocean of air, a 1 atmosphere pressure that our bodies are perfectly calibrated to. This external pressure helps keep our bodily fluids in a stable, liquid state. The atmosphere on Mars is less than 1% of Earth's. It is, for practical purposes, close to a vacuum. If a colonist were to be exposed, consciousness would fade in seconds as gases in the body expanded and moisture rapidly evaporated. Rescue would need to be immediate. This is why even a short walk outside demands a fully sealed, pressurized suit, not just to provide air, but to give the body the gentle, invisible embrace of pressure it quietly depends on. A self-sustaining Martian colony would, over centuries, inevitably develop its own unique language and culture. A community of people, isolated from their home world by millions of miles and a long signal delay, cannot remain a simple copy of that world. They would be a founder population, a small group of highly technical, resilient people living in a completely alien environment. Their very survival would depend on a shared experience unlike anything on Earth. New words would be invented, Martianisms, to describe the unique concepts of their world, the soul lag, the dust, the kinds of ice, the various types of habitats. Their art, their music, and their stories would be about their home, a world of domes, canyons, lava tubes, and blue sunsets. As generations passed, as children were born who had never felt Earth's gravity or seen a blue sky, this cultural drift would accelerate. Their language, their values, and their identity would diverge, slowly, soul by soul, until they were no longer simply humans on Mars, but a distinct branch of human civilization. The aesthetic and psychological importance of art, windows, and green spaces will be as critical as life support. We are not just machines that require air, water, and calories. We are emotional beings who require hope, beauty, and a sense of connection. In the sterile, cramped, and windowless environment of an early Martian habitat, the psychological pressure of sensory monotony would be intense. A colony engineered only for functional survival will struggle. To combat the monochromatic sameness of the red desert and the grey metal walls, the colony must be designed with the human mind in mind. There must be illusions of openness, high-resolution windows that show earthly forests or oceans, communal spaces painted in warm colours, and, most importantly, bright green botanical gardens. These parks would be the psychological heart of the colony, a place to go to smell soil, to see leaves, and to remember, in the midst of an alien desert, the feeling of the world that birthed them. One of the wheels of the Perseverance rover has been carrying a pet rock for almost all of its mission. In early 2022, as the Perseverance rover was driving across the floor of Jezero crater, a small, unremarkable Martian rock found its way into the rover's front left wheel, lodging itself inside the tread. And there it has remained. For months upon months, and for many kilometers, this small rock has been hitching a ride, a silent, rattling companion on one of the greatest journeys of exploration in human history. It has been seen in the rover's hazard camera images, a tiny, accidental passenger. There is something quietly touching in this, a small, unintended piece of companionship. The rock is, of course, just a rock, but it feels like the rover's first, unconscious act of collecting, a decision, by chance, to pick up a piece of this alien world and simply keep it close for the long, quiet drive. Becoming a multi-planetary species may be a kind of final exam for any intelligent civilization. We look at the long, dramatic history of life on Earth, a story punctuated by catastrophic extinction events, asteroid impacts, and supervolcanoes that have reset the biosphere again and again. As a species, we are, for the first time, technologically intelligent enough to understand this cosmic fragility. We know that a single, sufficiently large asteroid impact could end our civilization, and perhaps our species, in an instant. This leads to a sobering thought. Perhaps the universe is full of one-planet civilizations that developed intelligence, but never managed to spread beyond their home cradle before the next, inevitable cosmic catastrophe erased them. To colonize Mars, therefore, is not just an act of exploration. It is an act of long-term self-preservation. It is our attempt to pass the test, to become the first life from Earth to secure a foothold in the wider cosmos, ensuring that no single bad day can end our entire story. The first human sounds on Mars will be the breaking of a 4-billion-year-old silence. The red planet is a world of deep quiet. The thin atmosphere is incapable of carrying sound over long distances, and the planet's geology and weather are muted. A whisper of wind, a faint shifting of dust. For its entire history, for billions of years, it has been a nearly silent world. The arrival of the first human colony will change this forever. The first sound will be the rumble of landing engines, a brief, fiery noise the planet has never known. But after that, the new sounds will be the sounds of life, the hum of the habitat systems, the whir of a 3D printer, the soft music in a common room, and most profoundly, the sound of a human voice, laughing, speaking, and singing in the thin pink light. We will be bringing the quiet noise of life to a world of silence, and in doing so, we will gently transform it from a purely geological museum into a lived-in home. And so, our journey through the quiet, russet world of Colonizing Mars comes to a gentle close. We have drifted through the 7-month void, crossed the chasm of silence, and stood, in our minds, upon a world of profound, cold beauty. We have imagined the first human footsteps in the iron-rich dust, and the first blue sunset painting a sky that is not our own. The challenges are immense. A world of thin air, toxic soil, and a distant, pale sun. But we have also seen the quiet ingenuity that will meet them. The small golden box breathing out oxygen, the robotic hands printing shelters from the ground itself, and the search for the lava tube caves that wait to offer sanctuary. These are stories of the future, but they are also a meditation on the present. The ideas of a new calendar, a new culture, and the sight of our own blue home as a single distant star are not meant to trouble our rest. They are gentle reminders of the vastness of time and the incredible, patient resilience of the human mind. The red planet, sleeping in the dark, will continue its long orbit. It will wait for us, whether we arrive as explorers, as pioneers, or simply as dreamers carried on the soft, slow currents of our imagination tonight. Let these grand, quiet thoughts become a cradle, a backdrop for your own deep rest. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of colonizing Mars and the gentle music carry you softly into rest. Sleep well. Good night.